All right, good morning and welcome to one of the first sessions of POPL 2023 here in Boston. This session is about automated verification. All three talks in the session are about concurrency. The first one here is about memory models and concurrency using clean algebra with tests. Our speaker is Michalis Kokologiannakis.
All right, thanks a lot, good morning. Thank you everyone for joining me for this talk. I'll talk to you about Cutter, which is our tool that automates weak memory model Metatheory. And before telling you what Metatheory is that we automate, I'll briefly talk about what weak memory models are, why we care about them, and what kind of properties we want to automate. So this is the message passing example. I have two threads. This left thread is a publisher thread. The right thread is a subscriber thread. I have two shared variables, data and flag, initially being 0. And the publisher sets 42 to data and then sets a flag. The subscriber reads the flag and then ensures that the data that it read is 42. Is this program safe? If we think about this naively, then the answer seems to be yes. But in reality, the answer is that it depends, and it depends on the platform that we run this on the CPU, the compiler, and so on. Just to give you some examples, this is indeed safe under sequential consistency or x86, but it is not safe under ARM or C11 if I compile this with relaxed accesses, because under these two last platforms, the instructions of the first thread can be reordered, and in that case, the subscriber might read 1 for flag and 0 for data, the initial value. Now, this is where weak memory models come in. So a weak memory model, or a memory model in general, is something that specifies the values that the program loads can read. So if I want to reason about a program like this, I have to assume a memory model and then take this into account, for example, when I verify this program. Now, how do we specify semantics under weak memory? Viktor talked about this morning. There are two ways to go about this. One way is to do this operationally. So suppose I care about x86, for example. I can devise an operational semantics that explicitly models things like CPUs, store buffers, and the main memory, and then use this operational semantics when I reason about the program. This is not what we do. We use declarative or axiomatic semantics. And in declarative semantics, the semantics of a program P under a model M is a set of execution graphs G coming from the program, such that each of these graphs is consistent under M. Now, how do these graphs look like? They look like this. This graph here corresponds to the execution of the message passing program that I showed you before, where the assertion is violated. So for example, this is the publisher thread, write to data 42, write to flag 1, read 1 for flag and 0 for data, which violates the assertion. As you can see, the nodes in these graphs correspond to instructions. And then I have edges that denote various relations between the instructions. And three standard edges that are included in execution graphs are the PO, or program order, which connects events of the same thread, and also the initializer event to the first event of each thread. This initializer event basically models the two initializing rights to data and flag. I just use a single event for brevity. Another standard relation is the RF relation, or reads from, that shows where reads are reading from. So for example, this read there is reading from this write 1. This read of data is reading the initial value. And another standard relation is the modification order, or MO, which is a union of strict total order. The strict total order is basically each of these totally orders same location rights. So in this case, the initial write to data is ordered before this write to data, and the initial write to flag is ordered before this write to flag. So this is how these execution graphs look like. What does it mean for a graph to be consistent? Well, each model basically restricts the shape of these graphs, restricts how they look like, and it does this by defining some extra relations and, for example, demanding that certain combinations be cyclic or something like that. In this case, if I want to forbid this behavior, I can define this new relation called FR that basically says that the value that this read is reading is overwritten by this, right? And then have my model forbid cycles like this one here involving PO, RF, and FR. And I can write this declaratively by saying that my model M demands that this transitive closure of PO, RF, and FR be reflexive. Just a fictional memory model. So this is how declarative semantics work, and this is how we can use them to model the semantics of concurrent programs. Now, in the past few years, there has been a long line of work that tries to answer questions on memory models. Questions like, is a model A stronger than a model B? So if I have a graph G that's consistent under A, does this imply consistency of the same graph under B? Is a compilation scheme from A to B sound, or is a program transformation sound for a model A? And in fact, answering this questions hasn't been easy in the sense that it has proven to be quite error-prone. And take C or C++, for instance, there has been a number of papers defining or refining the memory model, reasoning about why optimizations work or why they do not work, or why sequential consistency is broken, and so on. So these questions actually require quite a bit of work and quite a bit of expert work, in fact. And this is where this paper comes in. So I'll talk to you about Cutter, which is a sound complete but also automated way to answer questions like these. And using Cutter, we were able to reproduce a number of positive and negative literature results. The most interesting of which, in my opinion, is that the original compilation scheme from C11 to power is broken. This was published in this paper in PLDI, and Cutter manages to find a counterexample for the compilation scheme in approximately 45 seconds. So in the rest of the talk, I'm going to talk about why it is that we can automate these sort of questions, how we do it, and then in the end, I'll give you a brief demo of the tool if my computer cooperates. So in this declarative framework, most models can be expressed as the irreflexivity of some relation E. For example, sequential consistency demands that this transitive closure here be reflexive, PORF and MOFR. The precise definitions are not that important. x86 is slightly more complicated. As you can see, it does not include PO, but it includes some restrictions of PO. So this here says PO starting from a read or a fence. This is the identity relation of the graph events that are either reads or fences, or PO that ends up to some write or a fence, and then takes RFE and MOFR and so on. So most models can be written as the irreflexivity of V in this form. And what we observed is that E is not just any relation that we can write in relational algebra, but rather it's an expression in clean algebra with tests. So the key idea of this paper is that we can reduce memory model queries to language inclusion between cat expressions, which is decidable. Right? And very, very briefly, cat can be thought of as some extension of regular expressions, but this inclusion is basically inclusion between NFAs. Right? Now, for example, suppose I want to prove that sequential consistency is stronger than x86. Right? Then, as we saw in the previous slide, I need to show that the consistency of a graph G under SC implies the consistency of the same graph under x86. How does consistency under SC look like? Well, it's basically this thing here. And for x86, it's this. So I basically want to show that the irreflexivity of ESC, which is this thing here, implies the irreflexivity of x86, which is this. And the paper shows that in order to show that, it's sufficient to show this. And why? Very quickly, suppose that this holds. I want to prove this implication. Suppose this holds. I need to show that EX86 is irreflexive. Proof by contradiction. Suppose that there is a cycle in EX86, but now because of this inclusion, this is also a cycle in ESC, which breaks my assumption. And more generally, this is our soundness theorem. If I want to prove that irreflexive A implies irreflexive B, it's sufficient to show that B is included in A. And with that, I can actually answer all the questions that I showed you before because these were actually these sort of irreflexivity implications. All these questions I had before are irreflexivity implications. And this is the main takeaway from this paper. This is the main idea. If you want to remember one thing, is that we reduce these sort of irreflexivity implications to language inclusion. The only thing is that this is sound but not complete. So in my last slide, I want to show you how we get from this, how we get completeness from this. Now there are 3 different completeness issues. The first one is that I might get a counterexample that looks like this, right? So suppose I'm trying to prove some implication like this. I'm trying to show some inclusion, and while trying to show this inclusion, I get a counterexample like that. Now, if I interpret this example on an execution graph, this basically says that I have some event that for which T holds, some predicate T holds, then I can do some E path, and then because this should be an irreflexivity violation, for the same event, the complement of T holds, which cannot happen. And the problem is that what I actually want to show is not this inclusion up there, but I want to show that the intersection with the identity relation is included in that other intersection. And because clean algebra with tests does not support a concept like the identity relation, I use this same ends thing here that will basically give me the words in B that start and end with the same predicate. It will never give me counterexamples like this. So this solves this first issue. This same end solves this first issue. The second issue is that I know that the irreflexivity of AB implies the irreflexivity of BA, but then clearly BA is not an AB. And the problem with this is that the inclusion that I'm trying to prove does not take rotations into account. So to fix this, I simply take the rotational closure of the right-hand side. So if AB is in my right-hand side, also BA is going to be in my right-hand side. And this is enough to fix the second issue. And the final issue is that I know that irreflexive AA implies irreflexive of A, but then A is not included in AA. And in order to fix this, I do the same trick that I did before, similarly to how I took the rotational closure before. Here I'll take the deduplication closure. So if AA is in my language, A will also be in my language. And if I do that, then I get completeness, soundness, and completeness. So irreflexive A implies irreflexive B, if and only if same ends of B is in the deduplication closure of the rotational closure of A. Right, and that's all I had. That's all the slides that I have. Let me try and show you a demo of how the tool works. So here, on the left-hand side, I have 2 definitions of the array model. And the precise definitions are not that important, but very quickly, the first version of array defines HB to be PORF plus, and then array is this disjunction. The second definition takes some restrictions of PO, to writes or from reads, and defines array2 to be this disjunction here. And these 2 definitions are equivalent. So let me try and prove this with Qatar. I'll try to prove the first direction first and then the other one. So if I run this, I get a counterexample. And the counterexample, this is an inclusion counterexample. It basically says that the left-hand side, so this array thing here, can take an RF internal step, and the right-hand side cannot. Let's see why. The left-hand side can do an HB, from which it can take an internal RF step. The right-hand side can also take this HB, but then there's no RF internal, there's just RF external, and all the other clauses here do not have an RF step. But if we see this a bit more carefully, this is actually the first completeness issue that I showed before. So I'm not using same ends here in what I'm trying to prove. So I should write this, that same ends of array is in array2, but then the implementation uses a slightly different notation, uses that. Let's see how to save this. I had to use nano for this. Okay. So if I run this, I now get a different counterexample. And this counterexample now says that the left-hand side can take an arbitrary PO step. This is a true test, can take PO, and then again true test, which makes sense because of this PO. The right-hand side can only take specific PO steps. And now this is because Cutter doesn't know that the universe, like I have only two types of events that I care about, reads and writes. So if I restrict what I'm trying to prove to reads or writes, then it should be able to get rid of this counterexample. If anyone knows how to save in Nano without exiting, let me know. And then I get a different counterexample that says that the left-hand side can take a PO step and then an MO step, which can happen because of this clause here, PO from HB and then MO. The right-hand side can only do a PO here and then nothing. And this is the second counterexample that the second completeness issue that we saw before. It's because I'm not taking rotations into account. So if I take the rotations of the right-hand side as well, and then run Cutter again, then it manages to prove this. And I can also do the other direction. So just for completeness. So it proves this example. Now, the last thing I want to show you, this last example, is a compilation proof, how we can use Cutter to do these compilation proofs. So here I have I'm trying to prove compilation from RC11, a recurrent version of C11, to x86. I'm including the definitions of these two things, just to show you how these things look like. This is the definitions for RC11. It's a more complicated model. This is for TSO, right? So now if I run Cutter on this, I get a counterexample. And this is not because I'm not using rotations or deduplication closures and so on. It's not important for this one. The counterexample that I'm getting is because I haven't actually provided a compilation scheme, right? So for those of you that are familiar with a model, the counterexample that I get is precisely a write followed by a read, which is an ordering that's not preserved in x86 by default. So I have to, when compiling from C11 to x86, I have to insert a fence between these two types of events. And the compilation scheme is given in form of this assumption here, which says that basically when there's an SC write followed by an SC read, then put a fence in between. Then if I save and run this again, then Cutter manages to prove what I wanted. So this is all I had. I've presented Cutter, which is a sound complete and automated way to answer these sort of memory model meta-theoretical questions, which boil down to implications. Using Cutter, we managed to reproduce a number of positive and negative literature results. And as a bonus, for which I didn't talk about, but this is in the paper, if you're interested, please go ahead and take a look at the paper. We can also use Cutter as a meta-programming tool to generate consistency checking code for a state-of-the-art stateless model checking tool. The paper and the artifact are available there. If you're interested, this is the end of my talk, and I'll be very happy to take your questions and feedback.
All right, we have time for a few questions. Maybe Jens first.
Okay, hi. Oh, hi. I'm Jens Paulsberg from UCLA. Wonderful stuff. Could you point out in your sequence of examples a place where you really take advantage of having cats rather than regular expressions?
Sorry, can you repeat the question? I couldn't hear it.
Yeah, I would like to hear a place where you take advantage of having cats.
Of having cats?
Clean the algebra with tests. So as opposed to only supporting regular expressions. So you had many, many examples where you check this and that. Just point out a place where it's really important that it's cats.
I mean, the definitions of the model use these sort of predicates, which are not supported by regular expressions, right? So we need cat to support these predicates, this restriction of PO from writes, for example, or to reads and so on. You cannot write this with regular expressions.
Another question back there, I think we had earlier.
Hi, this is Umang from the National University of Singapore. So I see consistency checking. That's not a meta-theory question, right? It's a question that you have to answer for every trace.
Sorry,
And
I'm
I asked
not
that-
able to hear the question. Can you speak up, please?
I see consistency checking as a byproduct of
Right,
meta-theory.
yes.
Consistency checking, although, is not like a meta-theory question. It's more like you have a trace and then you want to check if it's consistent.
I missed the last part, sorry.
Consistency checking is not
Or if you can repeat the
necessarily.
question.
Checking is a per program or per trace.
Right.
But this doesn't seem to be doing that. So what's going on?
So basically, this generates the code that does the consistency checking for you, right? And then it uses a meta-programming tool, and it generates the code that, given some graph, will do the consistency checking. And it does this by basically interpreting the execution graph as another automaton. You have your memory model as an automaton as well. And then you take the product to do the consistency checking and find violations in your graph. But it's not that this generates the code that will do this for you.
I see. So is the size of the code really, really large in terms of the original?
The size of the
trace?
code is linear to the size of the product of the two automata, where the one automaton is the execution graph and the other one is your memory model.
I see. So so when you say consistency checking, you mean the graph already has PO, RF, and MO. All these
Yes,
things.
the graph has the standard relations built in.
Okay.
Yeah. Then you calculate all the extra ones.
Okay. Thank you.
We have time for one more right here.
Thank you. So my name is Jiun Kang from KAIS, Korea. So I'd like to ask the question of the models consisting of multiple irreflexibility checks. So I believe that usually models have multiple such conditions, irreflexibility conditions. So in order to prove the entailment between the two models, then you need to reason about the relationship between multiple irreflexibility checks and the multiple irreflexibility checks. How do you do your model or do your system scales to such problems?
So if I heard correctly, the question is that you might have multiple irreflexivity constraints, then you can usually transform this into a single irreflexivity constraint. Right, so even if you have multiple in your model, you just transform this. If I want multiple relations to be acyclic, then the union will be acyclic as well. So I just demand that have a single reflexivity constraint for each memory model.
We can actually do one more in back while we're waiting for the virtual speaker to log on. Do you see the gray sweatshirt far back there?
Hello, I'm Thibaut Parami from Cambridge, and my question is how much knowledge your software has of the base relation, and how hard would it be to add new base event and new base relation to accommodate models that are not just about read and write?
Did you hear the question?
So he was asking sort of, I had the same question, sort of how much is baked in about what these different relations are, and what is the work to add a new primitive relation? Did I
Right.
ask the
So
question
we have
correctly?
some,
This is Jens's question maybe also, because sort of what's the built-in knowledge here?
Right, so Cutter has some built-in theory that includes standard relations, the ones that I showed you before, like PO or F, MO and FR. And then the user can define, you can write things like declare a new relation that you care about. But then if you know, to proceed with some proof, you'll have to provide extra assumption. For example, you know, if I define my custom RF, right, then the cutter will not know anything about with which other relations this composes. So you'll have to provide assumptions written in cat form. For example, that you know RF does not compose with itself, right? So you write these assumptions in cat form. Some combinations are empty, some combinations are invalid, some combinations are a subset of the identity relation, and so on. And then you're usually able to proceed with your proof.
Okay, let's thank Michalis one more time.